Welcome. So this question says a 5 Tesla magnetic field is directed along the positive z-axis. A 4 kilogram a 4-loop coil carries a current of 3 amps and has an area vector given by 4I plus 0j plus 1k square meters. And then what is the vector torque experienced by the coil? So first of all, let's just remind ourselves that in this course X is always, usually to the right along the page. Y is visualized as being vertically up the page, positive Y. And our Z is, positive Z is coming out of the page. So that's our orientation. And so when I imagine this 5 Tesla magnetic field directed along the positive Z axis, I'm envisaging something which is coming out towards me. And it's going to be 5 Tesla. So that would be no X component, so 0I, and no Y component, so that's 0J. And it's got a component of 5 Tesla directed along the positive Z-axis, so that would be plus 5K, and that would be Tesla. So this is a IJK representation of the magnetic field, and that is given by that magnitude and that direction, and that skill of being able to go from the words to a visualization and then to be able to represent it as an IJK vector is, I think, really important. In terms of the area vector, we actually gave the area vector. I'm just going to kind of draw it at some angle, and that is going to be 4I plus 0J plus 1K, and that's going to be in square meters. You don't have to get the direction, factually correct. It's just good to have a representation of an arrow which is not, perpendicular to or in line with, or so some reasonably average, I want to say vague direction. Try to avoid doing it on an axis. Just pick a direction and draw it so you can think about it. Unless it's easy to draw. If it's easy to draw because you know exactly where it's pointing, then do it as best as you can. But if it's not easy to draw, just pick a direction. But what does this represent? This represents the axis which is perpendicular to the coil. So that's a 90 degrees. It's a bit like we did with Gauss's law, where we invented these area vectors which were at 90 degrees to our Gaussian surface. Well, now we're inventing an area vector which is at 90 degrees to our coil. Now, there's two possibilities, of course. There's one possibility where it goes to the right, and there's another possibility which is also at 90 degrees to the coil, where it would go kind of like down and to the left. So how do I know which one it is? And I can tell which one it is by using the so-called right-hand corkscrew rule. If my current is flowing in that direction, there's my current, then my area vector is pointing in that direction. And I can show you with my hand, where you take your right hand and you kind of put a thumbs up, and your finger direction represents the current direction around the coil, and your thumb represents the area vector. Or you can look at it and say, look, that current is going in a counterclockwise direction, and that means that my area vector is coming towards me. And if the current was going in a clockwise direction, it would mean the current was going away from me. Either way, you learn how to do it. It's important that you know how to do it. You want to get this the right way around, but with a bit of practice you can get it. And then what is the size of the current? And the current is, let's have a look, the current is 3 amps. So that's going to be 3 amps. And then the last little piece of information I'm given, maybe it's relevant, maybe it's not. In this case it is relevant, is that this is not just a single loop, it's a coil. And so I have, in this case, I think it's something like 4 loops. So the wire goes around 4 times, and the torque I get from the first loop will be matched by the torque I get from the second loop. because it has the same area, the same current, and it's in the same magnetic field. And that'll be matched by the torque I get from the third loop. So and so on. So just from my physics intuition, I can recognize the fact that I gotta take into account the number of loops. I can't just ignore the number of loops. If the current loops through the magnetic field again, I get another similar sized effect. So what is the relationship between these things? And the relationship between these things is that my vector torque is equal to, well, we just said the number of loops times the current times A cross B. And throughout this magnetic field chapter, we've noticed that every time there's a cross product, the magnetic field is at the end. So then I turn around and say, okay, let's do this. It's an IJK vector. It's a cross product. So let's just do this. So remember, with cross products, the order is critical. So I start with A. So let's draw at A. So it's 4, 0, and 1. And that is my A vector. And then I look at my B. And my B is going to be 0, 0, and 5. And then I'm ready to do my cross product. So A cross B is equal to. And what I do is, if I'm doing this on a piece of paper, I will literally put my thumb over it, but for you guys I'm going to show you it by simply marking the column. When I'm looking at that first column, I ignore it and I cross multiply the other two. So that's 0 times 5 is 0, minus 0 times 1 is 0. So that's 0. So that's 0i. There's no x component in this cross product. And then I remember to put a positive sign down, a negative sign down. Sorry, I'm racing ahead. Then you always put a negative sign down. That's a negative operator. When you're dealing with the J column, you always put a negative operator down. And so we have this. We put our thumb over the J column and we cross multiply. So that would be plus 20 minus 1, minus 0. My brain's not working so well today. So that's 20J. And then I put a positive operator down because we've got to add on this last term. And I move my thumb and I put my thumb over that column. And I say, okay, 0 minus 0. 0, okay. So that's my cross product, and just by the way, get used to putting your units down, so that would be Tesla meter squared. But what I really want is I want my torque vector, and that is equal to N I A cross B. Well, N is 4 and I is 3. 4 3s are 12. It's just 12 times this. So that would be 0 times 12 is 0i. And that would be minus, and 20 times 12 is 240. And then 0 times 12 is 0. So that would be 0j. Okay. And then units, it's a torque. So it would be Newton meter. So here we have it. It's a cross product, and the two kind of wrinkles were, does the number of loops matter? And logically, you can see that it does. And then the second kind of like a complication is, given words, can you visualize a vector, and then can you represent that vector as an IJK vector? And that's practice. So there we have it.